Hi, my name is Keyi and I'm part of the electrical sub team at HURC. And today I'll show you guys how to make a custom PCB. And for some of you, this might be your first custom PCB, so it's very exciting. This PCB it will be a converter. It will take an input of 5 volts and it will convert it down to a output of 3.3 volts. And you might wonder why exactly we need that. Well, imagine a scenario where you have a sensor that takes 3.3 volts as its power or as its logic. It requires 3.3 volts. And you only have a battery that gives 5 volts. So if you directly connect these two components, you risk burning out the sensor or you risk giving inaccurate data. But if we slot our little voltage regulator between it, it'll regulate whatever voltage input for. It could be 5 volts, it could be anything. In this case, we'll keep it at 5 volts. It will take that input and it will regulate it to a stable 3.3 volts so that you can use it with a sensor, you can use it with any component. So the start of any PCB design is to have a PCB designing software. And what we use today is KiCad. KiCad is very popular. It's, I think it's open source and it's free. So if you search KiCad, you open the link and you should be able to download it for any operating system. And feel free to slow down the video, stop the video if you need, but I'm gonna go right ahead. Once you open KiCad and download it, you should be able to create a new project. And beware of the save path of these projects. We will figure out CashCAD eventually with you guys, but for now, I think it's not a bad idea to just save it somewhere in documents as a one-off. So I'm gonna name it 5 volt to 3.3 volt converter. And as another note, 3.3 volt can also be written as 3v3. Okay, so now we have a new project. And the first part of any PCB is to make the schematic for it. And the schematic is kind of like the blueprint of it, but it's literally just the electrical, like what is connected to what. And it doesn't have any bearing on the physical location of components. It just knows that these components are supposed to be connected. We'll actually make those physical connections in the PCB editor, which is the step after this. So when you open the schematic editor, which should be the first selection in the menu, you're going to see this blank page, which is where your work. In this blank page, you can place symbols by going to place. You can also press A to place symbols. And it may take a little while if it's your first time opening KiCad, but within here, you have access to a lot of general symbols to represent stuff. So let's first place a resistor. There actually isn't a resistor in this circuit, but let's just place one. So as you see, my mouse is hovering with it, and wherever you click will be where it's placed. If you click again, while the little symbol is on it, it will bring up choose symbol once again. And the way to get rid of this is just to right click and then cancel, or click escape, and then you're back to a normal cursor. That's just to remove the symbol selection mode. To navigate around this sheet, you can scroll in, scroll out, and you can right click to drag. Okay, and to delete a component, I personally recommend left click, drag, select all the components, and delete. So the first part of this PCB is an input of 5 volts. So you need somewhere to input it to. Let's do an input method of PCB, of USB. So we're gonna make a USB port on our PCB. So if you go into symbols, once again, you can search USB and _C, _C. And you'll be able to see some good options. Yeah, I think this one is fine. So the don't be scared. It looks a little bit overwhelming. But that's because it looks overwhelming because USB-C, as many of you know, it can both charge your computer while also transmitting data. It's really powerful. But today we'll only need it to we'll only need it for power purposes. So if you look closely, only ground, pin A1, and V-bus, pin A4, are necessary. Everything else is really not necessary. And the great freedom of PCB design is that if you don't need something, you can simply put a no connect on it. In the right side, you'll see a no connect option. So we just no connect, no connect, no connect, no connect. If you're more curious about these things, I think it's important. You can search out USB-C differential pairs and communication comms protocols. They're very interesting to read into. But yeah, besides V-bus, which is voltage, the V is voltage, and ground, you don't need any of these other pins because we're not transmitting any data. So we'll put no connects. And the reason we put no connects is because otherwise the software will run a rule check on your circuit and be like, these pins are not connected, or these pins are floating. You have to connect them to something. And this is our way of telling it we are deliberately not connecting it to anything. So that's our input of 5 volts. Very nice. And we also need an output after everything happens. So we need the output for the 3.3 volts. Now, I was going to use a USB, but Grant told me that USBs are not, the standard for USBs are not 3.3 volts, and you're not allowed to use that. So instead, we're going to use a connector. So if you search connector, you'll see these very standardized names. And it basically means connector, one row of one pin. So if we're doing power, then we need a ground pin and a voltage pin, or a positive and a negative pin. So we'll need one row of 2 pins. And you see there's a pin option and a socket option. So the socket option is what we're looking for because it would be, for now, let's use the socket option. The pin option would be 2 like male pins, and then the socket option would be 2 like female like things you can plug into. So if you double click on socket, you'll have a socket over here, and it will be our output. Awesome. Make sure always to escape so that you can have your cursor back. So now we have our input and we have our output. Now we actually have to do the voltage regulation part. So the voltage regulation part is pretty complicated, and that's why we offload the work. So if you go on this lovely website called DigiKey, it's a distributor for electronics. You'll be able to find basically any electronic product you ever needed. But today I'll make it easy for you. I'll give you the number that we're using. The part number is called the MIC5317. And this is an IC, or an integrated circuit, that does linear voltage regulation. So after you search it up, scroll down, and the first option should be there. When you click on it, you'll see the 3D model, you'll see, very importantly, the data sheet, and a bunch of other information. But the most important part is the data sheet and the models. So within the data sheet, you'll be able to learn about this chip. This chip is able to convert anywhere from 2.5 to 6 volts down to a stable 3.3 volts. And as a note, make sure that in the name it has 3.3. That's to show you that these are the type of regulators that will always go to 3.3. There's some regulators that go to 1.5, and there's some regulators that can be tuned. But today we'll be using this one. So within any data sheet, you'll be looking for the typical application circuit. So this is very important, as this is what you'll rely on. First, you see that we have the black box of everything that's happening in this integrated circuit, and we'll take the name of the circuit. And once again, we'll go into our symbol library. Just as we found the USB-C and we found the USB-C input and the 2-pin connector output, we will also be able to find, well, sometimes you have to shorten the name, but we will also be able to find the symbol for common voltage regulators. And this is all library within KiCad. So let's see, if you see 1.0, 1.2, that's not what we're looking for. We're looking for 3.3. So we double click, and there we go. Looks pretty similar, wouldn't you say? Cool. Now, we can't just operate it like this. As the datasheet told us, we need to add some capacitors on the outside. And capacitors basically operate as a filter for some of these signals so that you can get a consistent input and a consistent output. So VBAT would be in our case, the VBAT would be the USB-C, like the power we get from the USB-C. And then it would be connected in parallel to a capacitor. So let's do that then. Let's get a capacitor. Now let's learn to use our shortcuts. Press A, and you'll be brought up to the symbol library. If you search capacitor, okay, I guess capac works better. You'll see I like using C, the unpolarized capacitor. Place it, and you'll be able to do the connections that the datasheet told us to do. Specifically, one part goes to VIN, other part connects to ground, and obviously VBus connects to here, and ground connects to here. Cool. So this works. This works perfectly fine. This is a very direct connection, but one can argue that this is kind of a messy situation because it's not exactly messy. It's just as our circuit gets more and more complicated, it's harder to have these wires go all the way around the screen. So another way we can do this is by using these things called nets. So if we go to, not place symbols, if we go into place and we go into place power symbols, we'll be able to place plus 5 volts. This isn't saying that we're just generating 5 volts. This is categorizing the output of VBus as 5 volts, and we're tying these two things together. So you're basically saying whatever power you're getting from the USB-C, the positive side of that is going to be 5 volts, and we're going to call it 5 volts for the rest of the circuit. And it is true. So then what's the point? It's just going up to 5 volts. Well, now you can place this side up to 5 volts as well. And for a larger circuit, if there's not enough space for these two things to be together, this can be all the way on the side. And this connection from A4 VBus to the end of C1 is still a connection. You don't need a physical wire that connects all the way. Okay. Now we'll do the same thing with ground. And place power symbols can also be shortcutted via the P. So ground goes like this, escape, and sorry if I didn't show wiring close enough, but in order to wire, you need a clear, you need to not have anything selected on your cursor. You click one of these dots from coming out of a pin, and you connect it to a different dot. And that's a connection. So another convention to keep in mind is that power should always go up and ground should always go down. Do not do not do this. Do not do this. This is great. And if you do need to rotate anything for any reason, you can select the component and then press R multiple times. Yeah. Okay, cool. Now let's finish the circuit. Select the circle, connect it to ground. All right, nice. So now we have the other side of the circuit. So I'm gonna call this side of the circuit, I'm gonna call, obviously the output is not 5 volts because then it's just gonna jump from 5 volts past the IC, like it's not even gonna go through the IC. So that's not correct. So we'll rename this net, which makes it effectively a different net. If we call this by plus 3.3 volts, and obviously we draw the other side to ground, that's our output. So what are we missing? We go from USB-C up to 5 volts. 5 volts comes down through the capacitor, goes into the IC, and now we need a capacitor on the other side. So let's refer to the circuit again. As you can see, voltage goes in parallel to capacitor and goes into Vin, also goes into ground, obviously, creates a loop. And then the output capacitor is also necessary. And it will be basically the same thing. Go here, take 3.3 volts. And connect it all the way back together. So that's great. We have our input, we have our converter, and we have our output. And only 2 more things to note before we move on to the actual PCB design is, well, we are doing PCB design, but the PCB routing. If you look in the schematic, the EN pin is not connected to anything, and that's a sign we should use our no connects. So once again, in the corner, you take a no connect and attach it to EN. EN is a very interesting pin as it's basically an enable pin. So if you wanted to connect something else that would trigger the actions of the IC, you could do that. But today we're not. It's just going to be constantly, whenever it has voltage, it will convert it down to 3.3 volts. So another important thing to note would be within every component, if you double click, you'll be able to see its reference number, which is really helpful when you're looking at the PCB view of it and you can't tell what is what. So everything will have a reference, a value, which often becomes its name, and a footprint. So what exactly is a footprint? It's hard to visualize. So let me show you an example on Google. So if you do footprint versus schematic for PCB design, it's good to look at these pictures because in the schematic view, it's just a symbol with pins. But in the actual footprint, it will be what the physical component will be soldered onto. So basically, like, if you took a physical component and took all its connection points and put it down onto the PCB itself and soldered it down to the board. These red pads are exposed copper. And basically how PCBs work is it's just a sheet of copper and then a sheet of non-conductive material. And then you have a drill that drills out sections of the non-conductive material and it drills out paths within the non-conductive material. And then from the top, you can connect these things together. So it's almost like if you have a bunch of bushes and you draw a maze through it, and then you let a person walk through the maze. They can only walk that path that you've drawn. And a pad is an example of a path. I guess it's not a very good example, but it's basically the shadow of what it's actually going to look like. on the board. And so for every schematic component or schematic symbol, you'll need a footprint. So if you double click on any schematic, you'll be able to assign a footprint. You can do this individually, or an easier way to do this is to go to the top right, assign footprints, and it'll load. It looks like a lot, but do not worry. The center are all the components you have. The right are a lot of footprints. So let's go from C1. We know that C1 is the capacitor. And capacitors, if you search up capacitor PCB footprint standards, capacitors are very common. And they only come in certain like sizes. Yeah. So they basically come like little pills, and there's only a few sizes that there are. Specifically, they're called like 0201, 0402, 0603. The size of your PCB would limit the size of your capacitor, but today let's use 0603. I think that'd be fine. So for C1, we go 0603. And yeah, you'll be able to find these footprints. So I just did it very quickly, but if you select C2 and then go to the right side and you select, if you see capacitor, SMD stands for surface mounted device, which is exactly what we're looking for. A footprint is mounted on the surface. A footprint is what you use to mount things onto the surface, because you solder the component onto the footprint. 0603 is its size, or a code for its size. And when you double click, you assign it. So now we go to J1. What was J1? Well, you can see by the name that it was a connector, 1 times 2, a row of 2 pins, and it was a socket. So a common connector that we can use for this is called the JST connectors. So yeah, these are JST connectors. So then we'll need to take one of these guys, and we'll be mounting it. Mounted on PCB would kind of look like this. So before we're able to connect it, we actually need to make the slots on the board and the conductive and cut out the conductive material on the board to fit this on top of it. And that is what a footprint is. So we'll take a JST. If we search on the top, JST connector, and we'll take the 2.5 millimeters. And 2.5 millimeters is the pitch, which is the distance between the 2 pins. Yeah. So obviously, as the 2 pins get further apart, you'll have to like design a bigger space for when you solder them. Like this will have to be wider. Cool. So let's take the JST connector, 1 row of 2 pins, 2.5 pitch. Sounds good. Double click, and we assigned it. Now for the USB-C plug, we had to look through a few options, but I'm pretty sure we're going to use. The tough thing with the USB-C is that we're only using it for power, which is an uncommon thing. A lot of people use USB-C when they want to use it for data and power. So we're going to use this one. I've already linked it in the chat. Yeah, so double click and we're there. And lovely, our IC has already had a footprint done. So now let's go to the bottom right, apply and save the schematic. Click OK. And return to your schematic. So now every component should have a footprint. Let's just check real quick. if you left double click on a certain symbol, you'll see a footprint. Awesome. Cool. Okay, now control save, and we've just finished with the schematic portion. Now the next step is to convert it into the PCB so that we can actually physically arrange what the PCB will look like, because these are just the connections. Okay, you're halfway done. So now click on this little symbol, switch to PCB editor, and you'll see a screen like this pull up. And I know you don't see any components, so you have to manually go here to update PCB from schematic, which is pushes all the changes you've made in schematic onto the PCB screen. So once we click this, if you see any errors here, then the errors messages should come with a designator like J1C1. Just go to that specific component and check if there's anything unconnected, if there's anything connected too much. If you end up having problems, just ask chat or ask us. So I have no errors, no warnings. Awesome. So we update PCB. Never mind, there's many errors. Okay, this is a great example, solving errors. So it seems like the main errors are with P1. P1. Okay. So if we look at the footprint for P1, I'm guessing a lot of these errors are coming from, because we're, like I mentioned before, we're only using the USB for power. So a lot of these errors are coming from these pads, which are meant to connect to data. Like when you transfer like photos from your phone to your laptop and they're connected via USB-C, that's via these pins. And I'm not currently connecting them to anything. Like these pads are not being used within the schematic, because once again, I put them on no connects. So I think there's just some issue because my footprints do not match. Like in my footprints, all of these still have pads. They're just not connected to anything, which is fine. I think that's just a limitation of using something that's better. Like something that has more capabilities than we're using it for. Okay, so in the PCB editor, it's the same. Scroll in, scroll out, right click to drag around. Let's take our USB-C plug, and as you move it, you'll see these blue wires coming out of it. Those aren't connections yet, but they're trying to tell you what it wants to be connected to. So use these wires as your guides. And our goal right now is to not crisscross wires and to make every connection as straight as possible. So once you have this selected, you can press R and you can rotate this to give you the most optimal connection. So we also have to remember the order in which we did things. So we did things, the most optimal order would be the USB-C output is on the left side of the board, and the USB-C input is on the left side of the board, which takes 5 volts in. And on the other side of the board, there's the 3.3 volt output. Cool. So we're going to take this USB-C plug, then it goes to a capacitor, which make sure you select the whole capacitor before moving it. Rotate it a little bit so the wires are straight. And then it goes to the IC, the integrated circuit. I think I can rotate this a little bit. Yep. Rotate this. And final connection over here. Connector over here. Okay. All right. Looks mostly good. Cool. So now you see these lines are mostly straight. We don't need that much space, so sometimes if one of them is crossed, you just have to cross them all. Like you have to rotate them all a little bit. Okay, now all these connections are basically straight. Cool. Now you roughly see the shape of the board that you're going to make. So what we're going to do is on the right side, we're going to go to edge cuts. I'm losing where edge cuts is. Where's edge cuts? Oh, there it is. Okay, now we select edge cuts layer, which would be the actual cut of the board. We'll go to this, which is draw rectangles. We'll draw a rectangle that contains our entire circuit. Oopsies. Cool. And right click to cancel. And now we're gonna right click on this shape, go to shape modification, and let's fill it to make the sides a little bit rounder. Nice. Cool. And now, okay, cool. And now you've defined the basic shape of your board. A really cool step to see right now is if you go up here, you go to 3D viewer, you're able to get a little preview of what your board looks like. You see the edge cuts are done and the 3D models are loaded in. Very nice. Cool. So now it's time to make the actual physical connections, which are called traces. These traces will be via this wire over here. Oh, this selection. And basically what you're gonna do is just select a pad and run a wire to where it's supposed to go. While you're running this wire, you'll see like this is highlighted, this is highlighted. I can't connect this to B5 because based on our schematic, it knows that it shouldn't be connected there. So based on the logic of our schematic, it's going to guide us in where to go, which is pretty gosh darn cool. And you can see I can't connect it to anything else. It will basically avoid everything else. Cool. Our 5 volts, 5 volts, 5 volts. And then our 3.3 volts connected all the way. Yep. All right, now let's do our grounds. And obviously in more complicated boards, the ground and the 5 volts wouldn't even be on the same layer, but in this board it is. So make sure to leave appropriate distance to avoid shorting, which is just when ground and power find a path, a very easy path to each other, and then they don't go through the components that you want them to. This is kind of bad tracing, but I'm doing it very quickly. Okay, and trace it all the way back. And I think we're mostly done with everything. Yeah. Because these are, if you see the X, they're all no connects. Yeah. So now we can view it in 3D once again. Lovely. And you'll see little traces. And like I mentioned before, these are actually the physical millings because the top is a non-conductive material. And you'll see a drill that goes through it and drills down to the copper level, exposing it. And then what we do is solder the metal part of this to that copper layer. And it can't go anywhere besides to the next component because you define the path. Okay, awesome. And if you guys really wanted to, you can add some text like 5 volt to 3 volt 3 converter LDOC, and you can also add your names, stuff like that. And it should all appear when you actually send this board to be manufactured. Oopsies, I put on the wrong layer. That's the other thing. Text should be placed on the silkscreen layer. So yeah, let's put it on the silkscreen layer. Awesome. What I did there was I put it on the wrong layer, so it didn't appear. The silkscreen layer is where text is actually done, so it's not supposed to be on edge cuts. So what you do is you just double click your text, select layer, and then go to silkscreen. Awesome. So now it should appear in your 3D model. Yeah, and there's a lot of optimization to be done. For example, the capacitor should be as close as possible to the inputs and outputs. There's a lot of dead space here, but overall this is a pretty solid first design, and congratulations. Yay!